Ina charger isi na kayusi.
Nagamba wale wagaya kubulize charger wagana. Charger ntwale hivi. Mami hizo kweka. Baji kwa tamwa.
Baka jamu kwa nino saka katiri.
Mati kati charger hizo zizikole.
Ino ufuna katika nini na charger kwa hapa. Katika ya gamba tika. Ndio hizo kola. Kusuka nikafanya.
Eka wano gendo za nyavule.
Kama zipo. Yaani hizo moja basi kwa
Obogeno jagenda lyo chini akagali kango okunola. Yakwe muluka yangu ngeno lyo kachimi bakateekemu. Jet. Hello. Yabana gasi balaba. Enti bali mu Ada wakolera wakati.
Dia kama tumekuwa tulize vigaya tuliza wewe
Anga ga jebbe.
Ngako wanagera nje kukuangalia. Ngako wagamba kwa hivi na wagamba. Jebbe. Kuna msana.
Sakoje?
Ati ya muda bwana alianza.
Good afternoon, guys. You made the right ups of the notes I sent. I told you today we are going to start off with what we call calorimetry. And calorimetry is basically what you've heard of in senior 5, I mean in senior 3, senior 4, and it's where we had the specific heat capacities, if you recall, where we had latent heat. Yeah, if I may remind you, heat capacity is the amount of heat energy required to raise the temperature of a given body or a given mass of a substance by 1 degree Celsius or by 1 Kelvin. Then in case I'm to remind you about specific heat capacity is in general for a given mass, while specific only concentrates on only 1 kilogram what? Mass of a substance. So you would find that those definitions are key for someone to recall all the time. So one needs to know what specific heat capacity is and what heat capacity is. So, like I said, we are going to discuss what we call calorimetry. And calorimetry. Kasacha Hamza, you're not in class. You're not in class. Okay. Kasacha Ali, sorry. So this calorimetry aspect, like I've been saying, it involves the measurement of heat. We can determine the amount of heat energy. We can measure or we can deal with also specific heat capacities of different items. We can also deal with latent heats. Now, let me give you an example. When you look at some of the foods designed, have you seen cornflakes, oats, and the like? Most of those items are made from maize. And someone just mixes only. Someone just needs to mix only with hot water for them to be ready to eat. Yesterday, I was discussing with some entrepreneurs on aspects of how we can improve on the quality of items we have in Uganda. And one gave me an example of posho made in USA. That the posho made in USA only takes 2 to 3 minutes to get ready. And the reason is The maize they prepare to make posho is first steamed or first boiled for some time. So when they boil it, it means they are going to change its specific heat capacity. So if they change its capacity, specific heat capacity, it is very easy for it to get ready when someone wants to cook it. Others, if you look at electric poles, which have been well treated and well heated, they can be put in a bush, and if there is a bush fire, those electric poles do not get heated up. Reason, they were cooked for a very long time under oil. That's why when they are cooking them, the oil penetrates deep into the pole. So what happens is the specific capacity of that pole changes. So the bush fire, however much it lights up, it might not be in position to easily heat up that pole. So the pole remains when it's not affected. Reason being, its specific capacity has been raised. So when something is cooked or boiled for some time, the value of specific capacity will always change, depending on the situation. So some of you might see some things taking so long. Yeah. For example, if you take a consideration of an item like what? Maybe something like, if you see someone has cooked meat already, do you know why when people are making katogo, they do not cook katogo, they do not cook meat directly with matoke. Why? Because matoke has a different specific heat capacity from meat or from offals. So what we do, they first boil the offals aside for some good time, then they will come and pour them into the katogo or into the matoke they have. At the end of the day, that extra heat it's going to gain on top of the earlier boiling will easily make the meat or the offals in the katogo now also to soften as the matoke also gets ready. So all that they are dealing with specific heat capacity, though some of us don't put these things into consideration. But all that is physics about heat in terms of heat capacity. So the first definition is heat capacity. And we are saying this is the amount of heat required to raise the temperature of a body by 1 Kelvin or by 1 degree Celsius. And its SI unit is joule per Kelvin. Then the other one is specific heat capacity. Now, specific heat capacity is specific in a way that every different item has its own heat capacity. For example, there is specific heat capacity of ice, specific heat capacity of water, specific heat capacity of copper, specific capacity of aluminium, specific heat capacity of zinc. All those different items have different specific capacities. I've given you an example of food. But before even I go to food, most of you have been to these salons where they use spirit, or you've seen the sanitizers. Sanitizers are evaporating. Now, why do they evaporate? It's because they have a very low specific heat capacity. And that means if they have a very low specific heat capacity, that means also they have a very low boiling point. So their boiling point is low, so they just need a small amount of heat for it to be converted to vapor from liquid. That's why when the sanitizer is exposed in air, it can easily vaporize. Why? The surrounding heat is enough for it to convert its state from liquid to gaseous state. The same applies to spirit. Now, when it comes to ice, specific heat capacity of ice is 2100, a half of the specific heat capacity of water, which is 4200. So water, you require a given amount of energy to convert water than the amount of heat you require to convert water, or to change the amount of, to change the temperature of water from a given degree to a given degree, the amount of heat energy required is 4200 joules per Kelvin. Because what they will ask you, what does 4200 joules per Kelvin of specific heat capacity imply for water? It implies that you need to change the temperature of water And in that case, you need to use an amount of heat which is equivalent to 4,200 joules. If it's ice and you want to convert ice and change its temperature, the amount of heat energy you require is 2100 because its specific heat capacity is 2100 joules per kilogram per Kelvin. So with that regard, we can say this is the amount of heat energy required to raise the temperature of 1 kilogram mass of a substance by 1 Kelvin. Or by 1 degree Celsius. And its SI units is joule per kilogram per Kelvin or joule per kilogram per degree Celsius. So, by mathematical definitions, heat capacity is defined by mass times specific heat capacity. Which will give us M times C. So heat capacity is actually MC. Okay, so with that, we can talk about the methods of measuring specific heat capacity. Methods of measuring specific heat capacity. And the first method for solids, let's talk about for solids. You want to measure the specific heat capacity of matoke, of posho, of what? Of sweet potatoes. Some of you don't see where these things are applied, but you need to estimate the amount of heat you require to boil food every day, to boil milk, to boil porridge, to boil sauce. You need that given amount of heat energy known. If you know that heat energy, then perhaps you can predict how much charcoal you need. You might predict how much gas you need. You might be in position to predict whatever you need to use to see how best you can have these items taken into consideration. Okay? So the first one is the method of mixtures. The method of mixtures. And for the method of mixtures, let me take a screenshot for this, then I take you through, I'm going to take you through the derivation of the equations, but the write-up, I'm going to send it here. Okay. So you'll find that in the method of mixtures, one, we can have Let me first wait. I'm coming in with the share, with the screen share here. As we wait for the other to show up, let me proceed with the sketch. First of all, we need to lag our apparatus. Lagging means you're protecting it from external heat interference. So you put something to lag the experiment, or to put like a barrier, so that the experiment does not gain heat and likewise does not lose heat to the surrounding. So I can assume I have a liquid in here, then I have my solid, which is right here. Then this is my liquid, and this is the lagging. I've said the lagging is used to protect the system from external heat interference. So I'll have also to get a stirrer to help me stir up the liquid so that we have a uniform distribution of heat. I will also have a thermometer to give me the readings of the temperature changes we are experiencing. So this is called a stirrer. This is the lagging. This is the liquid. And this is the solid, whose specific capacity is to be determined. This is the thermometer. And then this is a copper calorimeter. Copper calorimeter. Now, a copper calorimeter of non-specific heat capacity C, copper calorimeter of non-specific capacity C, CC, is weighed and its mass of the calorimeter, is recorded. It is then half filled with a liquid of non-specific capacity. Specific capacity of the liquid can be Cl. The calorimeter is weighed and its total mass MT. MT is the total mass. Specific heat capacity of the calorimeter. This is specific heat capacity of the calorimeter. This is MC, mass of the calorimeter. You will find the write-up in the group. Then Cl is the specific heat capacity of the liquid we have there. Then we can get the total mass. MT is the total mass of the calorimeter with the liquid. Then the mass of the liquid can be got from total mass of the liquid plus the calorimeter minus, because this is total mass MT, minus the mass of the calorimeter. Then the initial temperature could be determined, which is θ1 of the calorimeter, and the liquid of the calorimeter and the liquid can be θ1. So when you record the initial temperature, then you lag the calorimeter now. After lagging it, a specimen solid of mass ms is brought into the calorimeter and is heated in a steam jacket up to a temperature higher than θ1. So until the new temperature becomes θ2. So that means the solid will attain a temperature also from θ1 to θ2. The liquid also will change the temperature from θ1 to θ2. Yeah? Then the specimen solid is transferred into a lagged calorimeter. So at first it was heated to a temperature θ2. Now when this solid is given a temperature θ2, it is now going to be taken into a lagged calorimeter here, where it is going to get a new final temperature. Final temperature of the solid will become θ3. So the solid came in with θ2, and now it is going to enter into the calorimeter when it is having a higher temperature than θ1. But at the end of the day, because what happens is, all of us have ever showered warm water. When you mix warm water in a basin which has cold water, you will find that the warm water you had in a percolator or in a kettle at 100 degrees Celsius, when you mix it with cold water, the temperature will drop so that it becomes appropriate for you to bathe. Those of us who want to bathe some warm water, you get very hot water, then you mix it with very cold water, not very cold, but cool water, because very cold requires ice at least. If you say very cold, it means it is somehow ice water mixture. Or we can say it's purely melted ice. So we can say cool water. So that coolness, you feel it's cold for you. So when you feel it's cold, you want to raise the temperature. So what you do, you bring in a liquid with a higher temperature, then you pour it into that liquid, and then you stir it up, and you get some reasonable temperature, higher than the cool water you had before. So even here, we are bringing a solid, which has a temperature θ2. But then, when you place it in a calorimeter, we are attaining a new temperature of the solid as θ3. But in actual sense, everything in the calorimeter also attains θ3. So that also the liquid has a final temperature of θ3. Now, in this case round, who is losing heat? In calorimetry, it's very important and sensitive for someone to know what gives out heat and what gains heat. If you can understand those two, then it is always very easy for you to predict whatever you want to predict. So to start with, who gives out the heat energy? What gives out the heat energy is actually the hot body we brought in at a temperature θ2. It is going to give out heat to what? To the water and to the calorimeter. Okay? So in that case, the solid loses heat. So heat lost by the solid is equal to heat gained by the water plus heat gained by calorimeter. So the heat, remember, if you look at this, to get the heat energy, this was heat capacity. So heat energy, I forgot to mention here, heat energy is equal to heat capacity times temperature change. So we shall have Ahil double A for Ahil. So we shall have mass of the solid times specific heat capacity of the solid times temperature change. Temperature change will give us θ2 minus θ3. Why am I saying θ2 minus θ3? The higher temperature for the solid was the one it came with, because it was heated up somewhere. Then we brought it into a liquid, and then we stir them together. Then the final temperature became θ3. So there was a temperature drop. So the difference is θ2 minus θ3 is equal to heat gained by the water or by the liquid, specific capacity of the liquid. Temperature change for the liquid will be θ2 minus θ1. Reason, the liquid was initially at θ1, plus mass of the copper calorimeter, specific capacity of the copper calorimeter, times temperature change for the copper calorimeter. This copper calorimeter was at the same temperature, just like the what? The liquid. So at the end of the day, we are looking for the specific heat capacity of the solid. So this will give us what? Mass of the solid, specific heat capacity of the solid, θ2 minus θ3 is equal to mass of the calorimeter of the liquid, specific capacity of the liquid, plus mass of the calorimeter, specific capacity of the calorimeter. I can factorize out their temperature change, θ2 minus θ1, which is the same. So finally, specific heat capacity of the solid can be got from mass of the liquid, specific heat capacity of the liquid, plus mass of the calorimeter, specific heat capacity of the calorimeter, times their temperature change, divided by the mass of the solid, which is known, times the temperature change of the solid. So this would give you an expression which you can always use in the method of mixtures to have what we call the formula for finding specific heat capacity for a solid. Any question on that? You can have that definition down. Take that right up down as I take a yawn briefly. Okay, any question on the derivation we have made? So that is looking at what we call the method of mixtures. I'm trying to see if I can access my WhatsApp so that I send my write-up. It's failing to show my WhatsApp. I don't know why today it's not displaying, but So, as we wait for it, the next one is what we call the electrical method. So for the electrical method, it has some sensitive items I need to mention here. This experiment, you've seen it in O level, but even in A level, people still make errors on this kind of experiment. So this is the solid. Also, this solid ends up being lagged. So this is our lagging. So this is the lagging. Now this solid is in a state of that is the thermometer. This is the heater. So this is the heater. This is the metal or solid. Then this is the insulating jacket. Or the lagging. Then this is the thermometer. So this is our battery. It has a switch. Okay. The diagram is okay, but people have a problem. One, they forget to close the switch. Two, sometimes they put the heater in space. Three, they forget to tell us that they drilled holes in the metal solid to create a hole for the thermometer and create a hole for the heater. Then also this shows that this is the voltmeter and this is the ammeter, but people switch. They put the ammeter here, then they put the voltmeter there. So be very sensitive on that diagram. Okay? Now, the procedure goes as this. I will send the write-up as well. 2 holes are drilled or bored in the metal solid. After drilling these 2 holes, what happens is the mass of the solid now is measured. Now, people make a mistake on the write-up. They say the mass of the solid is measured in ms without telling us that this solid is first drilled. So you first drill the solid before you measure its mass. So, for example, if it is this phone, you first remove the what? If it was this phone, you first remove the casing. First remove the casing, Then now you measure the mass of the phone alone. We want to determine the specific capacity of this phone. Yeah, maybe if there's another screen on top, you also remove that screen on top. Otherwise, if you just say mass of this phone is measured when it is with its jacket, then it would imply you have a mass of the jacket and the phone which is not catered for in your explanation. So we first drill the mass. So when you drill the mass, you leave holes there. Then after which, a thermometer is inserted in one hole, this one, and a heater is inserted in the other. The initial temperature θ1 is recorded. The initial temperature θ1 is recorded. Then, of the metal case, of the solid. Then switch, after measuring that initial temperature, this is when now we need to get heat starting to run through the solid. And how is heat supposed to run? It is supposed to come from the battery supply through that electrical circuit to the heater. But now the heater is off. Reason the switch K is not yet closed. So the next step is to say close switch K. Yeah, when you close switch K, what happens? Simultaneously switch on the stop clock to measure the time for which the heat is going to run. After some time, time T1 is measured. Time for heating is measured as T1, and the voltmeter readings initially after time T1 is measured. Consequently, also the ammeter reading after time T1 is measured or is recorded. Then the final temperature θ2 of the metal is recorded. The final temperature of the metal θ2 is noted. Having noted that, then we have heat lost by the heater, because the heater is the one supplying the heat. So heat lost by the heater is entirely equal to heat gained by the metal. Now that is for case 1. For case 2, whereby you know power is got from IV. Yeah? But power is work done over time taken. So work done is equal to IVT. So which IVT, work done, is heat energy. So the heat will be I1 V1 T1 is equal to the heat gained by the metal, which will be mass of the metal, M, I'm assuming M is the mass of the solid or metal. So this will give me mass of the metal times specific capacity of the metal times the temperature change, which is θ2 minus θ1. After heating it, θ2 is greater than θ1, plus small h. Small h is the heat we are losing to the surrounding because one side is open. Okay? So this will be equation 1. So small h is heat loss to the surrounding. Then, when you adjust the rheostat, remember this one had a rheostat. Let me take you back. This rheostat you see here. This rheostat you see here is meant to adjust the value of current and voltage across the entire circuit. So the rheostat is adjusted to obtain different settings or values of setting The new temperature θ3 of the metal is noted for a time T2. So the new temperature is noted. So I2, V2, T2 will give me mass of the solid, specific capacity of the solid. Now θ3 minus the original temperature θ1 plus heat loss to the surrounding. So we can solve these two equations simultaneously and attain the value of specific heat capacity. So this will give me, because these new currents are and voltages are higher than the original ones. Why are they higher? Because the new temperature is greater than the original temperature. So we shall have I2 V2 T2 minus I1 V1 T1 is going to be equal to MC of θ2 minus θ1 plus H. Sorry, this is supposed to be θ3 minus θ1 minus, open brackets, MC of θ2 minus θ1 plus H. To start with, we shall vamoosh H. When we vamoosh H, what shall we have? We shall have also to vamoosh θ1. So finally, this will give me MC into θ3 minus θ2 is equal to I2 V2 T2 minus I1 V1 T1. So specific heat capacity will be equal to I2 V2 T2 minus I1 V1 T1, all is over M into θ3 minus θ2, close brackets. But, so this is how we can get specific capacity using the electrical method. If T2 is equal to T1, that means if someone is taking the same time measured, then when you measure using the same time, you'll have I2 V2 minus I1 V1 brackets of T over M of θ3 minus θ2, close bracket. This would give us the specific heat capacity. That is, if you have taken into consideration the amount of heat energy to be measured at the same time. So this is the electrical method equation we can use to find specific heat capacity. Someone has a question, please you raise it before I can take you through an example. So an example. An electrical heater rated is placed in a well insulated metal of mass 1.0 kilograms at a temperature of 18 degrees Celsius. When the power is switched on for 5 minutes, the temperature of the metal rises to 34 degrees Celsius. Find the specific heat capacity. Find the specific capacity of the metal. This was UNEP 2013, number 5. So we have power, which is 48 watts. We have the voltage, which is 24 volts. We have the mass of the metal, which is 1 kilogram. Temperature θ1 is 18 degrees Celsius. When the power is switched on for 5 minutes, time it takes is 5 minutes. 5 minutes is the same as 5 times 60, giving me 300 seconds. Working in SI. The temperature of the metal rises to a new temperature θ2, which is 34 degrees Celsius. The question says, find the specific heat capacity of the metal. So heat lost by the heater is equal to heat gained by the metal. Sorry, heat lost by the heater is equal to heat gained by the metal. Now heat energy from the heater, I showed you from here. Power is work done over time taken, which confirmed that heat energy can be got from power times time, which is the same as IVT is equal to heat gained by the metal is mass of the metal, specific capacity of the metal, temperature change θ2 minus θ1. So C shall be IVT out of M θ2 minus θ1. On substitution, we shall have the power. IV is power. This one gives us power, which is 48 times the time 300. What is over 1 into 34 minus 18. Can you press the calculator and give me the value of specific heat capacity? Give me that answer.
900.
Correct. Gives us 900 joules per kilogram per Kelvin. So that is the method of electrical method we can use to predict the value of specific heat capacity of so that will give us that value. So we are left with two methods, and those two methods are one, method of mixtures for electrical method, and the one which they call the continuous flow method. I'll send some write-ups of them so that you can read about them. When we meet again, we are in position to have some of these ideas discussed from an informed point of view. And with that, we shall also need to put into consideration that, like I said, when we finish calorimetry, we shall go to, under this calorimetry, we have latent heat also. When we finish latent heat, that's when we shall go to other aspects, like Newton's laws of cooling, but those ones can come in any time. And then after this part of calorimetry, we shall think of going to another section. Then we shall come back to heat, if God allows, another time later. But for now, we can stop here for today, but let me send you the write-up and some numbers to try out. In case you have any questions, please don't forget and hesitate to send them out so that I can take a look at them. Oh, I did give you an example on method of mixtures, did I? Yes, question.
So what is lagging?
Lagging. Have you seen anything that is protecting electricity from reaching you? You see a socket, it has that outside casing of a plastic. It means the socket has been lagged, so that the wires which are live inside, you do not touch them or you don't access them. So that socket casing becomes a lagging. So a lagging is something which is a protective gear to help us minimize the heat loss to the surrounding. Okay? Are you getting me right? Okay. I want to give you another one example before we close. I've not given it to you yet. So as you download that, I want to bring in the last example of the day. I've sent you method of mixtures, electrical method, and the continuous flow method. So I want you to read through them so that next time I don't waste much time on sketching their diagrams. So this one says a solid of mass 30 grams at 100 degrees Celsius is transferred into water of mass 35 grams contained in a calorimeter of mass 50 grams at 10 degrees Celsius. The temperature of water rises to 25 degrees Celsius. Find the specific heat capacity. Find the specific heat capacity of the solid. Specific heat capacity of copper is actually 390 joules per kilograms per Kelvin. Specific heat capacity of water is equal to 4200 joules per kilograms per Kelvin. So we are having a solid of mass 30 grams. Solid was very hot. We transferred it very fast to water, which water is cool. And the water is in a calorimeter at a temperature of 10 degrees Celsius. So the calorimeter temperature, I can assume, is the 10 degrees Celsius. The temperature of the hot body is 100 degrees Celsius. The final temperature we shall attain is 25 degrees Celsius. So we have temperature changing from 10 to 25 and dropping for the body from 100 to 25. So this is called the equation statement. The equation statement. Heat lost by the solid is equal to heat gain by the water plus heat gained by the calorimeter. Calorimeter. I told you in calorimetry you need to understand what gives out heat and what loses heat. If you hold the baby you feel like he's at a warmer temperature. Reason being is overlagged. My friend was asking about lagging. When a baby is wrapped in those clothes, you see those heavy clothes they wrap a baby in, they are lagging the baby so that he doesn't lose heat. That's why when you hold the baby at the end of the day, you feel he's already warm. So you are at a lower temperature, the baby is at a higher what? Temperature. So heat starts moving from a region of high concentration to a region of low concentration. So the heat starts moving from the baby to you. That's why you feel the heat of the, that's why you feel the baby is hotter. If the reverse was true, if the baby was cold, it means it is you losing the heat. The same explanation gives the reason as to why when you step on the floor, you feel the floor is cold. Reason, you are losing heat to the floor. The floor is at a lower temperature and it's gaining heat from you. So if you understand those items, you'll always be in position to interpret calorimetry. Let me first take this call. It might be advantageous. Hello? Yes, madam. I'm okay, ma'am. How are you? Okay, so after that equation statement, heat lost by the solid is going to be mass of the solid, specific heat capacity of the solid, times temperature change of the solid from 100 changing to final temperature theta 3 is equal to heat gained by the water, mass of the water, specific heat capacity of the water, the temperature change for the water, which is going to be the water raises temperature from theta 1 to theta 3. So the change in temperature will be the higher temperature it has attained of 25 minus the 10, a plus mass of the calorimeter, specific heat capacity of the calorimeter, temperature change of the calorimeter. Water was contained in the calorimeter. We all enjoy ice cream, not so? When you're taking ice cream, you are experiencing these conditions actually. We are coming more to latent heat of vaporization. Yeah? Kankunda. Gloria, 3. So, I was giving you an example of ice cream. The ice cream you hold in a cup, the ice cream is cold, the cup is also cold. It means the ice and the cold and the cup are at the same temperature. That's why here we are saying the water and the calorimeter are at the same initial temperature, theta 1. Then after which, when the temperature has increased, there is a stirring of water in the calorimeter, so they are all at the same final temperature, theta 3. Okay? So this is theta 3 minus theta 1. So mass of the solid is 30 times 10 power negative 3 times specific capacity of the solid we are looking for times the temperature change. Theta 2 minus this will give me 75 is equal to mass of the water, which is 35 times 10 power negative 3 times 4200 times 15 plus mass of the calorimeter, which is 50 times 10 power negative 3 times specific capacity of the calorimeter, 390 times the temp temperature, which is 15 in change. I can lose this. Finally, can we make now specific capacity of the solid the subject? 35 times 4200 plus 50 times 390 times 15, all is divided by 30 times 75, by 15 once, by 15 two. Calculator, can you give me that answer? Someone compute that please and give me the answer.
One thousand 110.
Correct. 1110 joules per kgs per Kelvin. So we are handling calorimetry. That was an illustration on how we can have the method of mixtures handled. The other one was an electrical method, so you can have those examples downloaded. If someone missed the first ones, I can reverse the pages and you see what the questions were all about, or what we discussed was all about. Don't forget to update your notes because I've sent the write-up. Please do. Let me send the numbers here. Okay, finalize that and we can close off the meeting. Any questions? Any questions, please? You can experiment some of these ideas at home. You pour water in a cup, then the cup, which hot water is, I'm talking about hot water. You touch the surface of the cup, it will be hot, but with time, the heat is being lost to the surrounding. So after some few minutes, you can measure the different temperatures of the water at any one time. Okay? So if no questions, allow me to take this as an opportunity to close the meeting. And I would like to thank you for your attendance. Please, next time, do some read up on mixtures, method of mixtures, using the electrical method and the continuous flow method I've sent, so that we do the calculations well without having a lot of challenges.